So in this lecture, what we're going to do is we need to analyze what are called impulse and step functions. Basically, we need the a language to describe UDLs and step functions, or sorry, not step functions, UDLs and point loads. Okay, let's see. So we're going to build these things up quite slowly, and then hopefully you'll kind of see how these things help you model loads. So the first function we're going to consider is a switch that has two states, on and off. Suppose the switch is turned on at time x equals 0. We use the Heaviside function to model this. So the Heaviside function, the U stands for unit step because it has a value of 1, and there's going to be a step in the graph. Okay, so what this funny notation means that it tells you, like, what is a function? You have an input. To each input you associate an output. Now what you're kind of used to is a single formula for the output, but there doesn't even have to be a formula for an output. And here what you have is kind of two formulas. One if the input is less than 0 for negative inputs, and one if you have positive or 0 input. So if the input is negative, it outputs 0, and if the input is positive, it outputs 1. So let's see what it looks like. Okay, so first of all, at 0, well, let's say a small negative number, or any negative number at all, actually, it outputs 0. So the points on the graph, remember the graph of a function is equal to all the points of the form input, output. So if you put a negative number into this, you get out 0. So all the things, negative number along the x, 0 along the y. So for example, -2, 0. So all those points are all here on the negative x-axis. Now it's not too important, but at 0, the value jumps from 0 to 1, but when you're arbitrarily close to 0, so for example -0.0001, that still gives you 0. So how you show that is you put a circle not filled in at 0. So this indicates that it's equal to 0 all the way up to 0, but at 0 it's not equal to 0. Then at x equals 0, the value jumps, and at 0 the value is 1, and this you do a filled in circle. And then after this, so for example x equals 2, that's a positive number, you get out 1. So for all these values of x, the output is 1, so no matter the input, the y coordinate is 1. You can see it looks like a switch. Now if we wanted, you could join these up, but then it's not the graph of a function anymore. Often when we draw it, we will join those up. But this is your basic, this is called the Heaviside function, the unit switch, equal to 0, up to 0, and then it's switched on at, now here you could use t, but it's not actually going to be time, it's going to be distance along the beam. It's suddenly equal to 1. And you can see how this could be used to model a UDL over a portion of the beam. So we'll see it quite soon now, but say no load, and then suddenly there's a load. Okay. It's no problem writing down a switch that's turned on at x equal to 2. You just, the language is you shift it to x minus 2. Now we'll slowly show how this works. So this is going to switch on at 2, and at 2 it's going to be equal to 1. Let's get x and y. Okay. So say if I put in something that's less than 2, for example 1.5. So if I put 1.5 into this, I have u of 1.5 minus 2. And the point is, it doesn't actually matter exactly what the number is. It only really matters if it's negative or positive. And 1.5 minus 2 is negative. And when you give the unit step something negative, it spits out 0. And you can show if you put anything that's less than 2 into this, you get out a negative, because it'll be something smaller than 2 minus 2 will be negative, you get 0. So all the way up to 2, you're getting out 0. Of course, at 2, if you put in 2 into this, you get u of 0, but u of 0 is in here, the 0 is in here, greater than or equal to 0, so equal to 0. So if you put in u of 0, you get out 1. So we'll put this empty circle, and suddenly at x equal to 2, the value jumps, it's called the discontinuity, to 1. And then, of course, if you put in anything bigger than 2, for example, u of, say, 2.3, minus 2 is equal to u of 0.3, which is u of something positive. And when you give u something positive or 0, you get out 1. So for all these, say 2.3 in, 1 out, so it'll be 2.3 along the x, 1 along the y, 3.3 along the x, 1 along the y. You're going to get something like this. So if you want to switch that turns on at 2, you do u of x minus 2. Now you might be tempted to think that it should be plus 2, but here we've argued that it's not. So if you put in, so like say if I said delta was some positive number, u of something that's 2 plus something, 2 plus delta into this. So I'm saying x equal to 2 plus something positive, possibly 0 actually. And then you do the minus 2, you get u of delta, and u of a positive number gives you 1. Similar story, if you put an input here that's 2 minus delta, so smaller than 2, minus 2, the 2 minus 2 is 0, you get u of minus delta, which is something negative, and when you give u something negative, it spits out 0. So that's just an argument showing that if you're bigger than 2, or in fact equal to 2, it spits out 1, otherwise it spits out 0. You can combine these to write something that is on between 2 and 4 and off otherwise. Okay, so say put in x equal to 2, x equal to 4. Now, strictly speaking, I think in terms of the circles, now the circles actually don't really matter that much. It's just being a little bit fussy if you're like question what's happening at 2. But this function here, I think will be at 2, it's equal to 1. And I think actually what happens is at 4, you're going to get actually the value is 0. So there's a slight asymmetry, but it doesn't actually matter. So if you want to turn on at 2 and switch off at 4, you do plus to turn it on at 2, minus turn it off at 4. And you have to do it in the right order. Turn on 2 first, then turn off 4. So here you can see how you get something that looks like, oh shit, I suppose I shouldn't say stuff like that either. But anyway, so this bit shouldn't be here. Now, we'll just kind of go through it now. So really this is the graph of this function, but we're going to think of it actually like this, because we're thinking about it as like a UDL. So it's a UDL of 1 between 2 and 4. And, you know, we can go off then and I understand you draw this kind of crack. So a UDL between 2 and 4, 1 kilonewton per meter will be equal to this thing. Now what I want you to do is just to kind of convince yourself that this is the right thing, maybe substitute in x equal to 1.5 into this, see do you get 0. Maybe x equal to 3.1 into this, make sure you get out 1, and maybe x is equal to 4.2 into this, make sure you get out 0. It'll just be a little exercise for yourself to show that. Of course, the output doesn't have to be 1. Like you don't want all your UDLs to have a magnitude of 1, you might want them to have a magnitude of 18 kilonewtons per meter. So what you can do is you could have the output equal to 3 or equal to 4 by multiplying these things by scalars. So for example, 3ux is 3 times 0 for negative x, which is just 0, and then for positive x it'll be 3 times 1, which is 3. So we'll draw both of these. Now this is equal to 3. The scale will be a bit funny, but sure, how bad. And then the other one, sorry, this is out of scale, but what can we do? So this one is turned on at 2, switched off at 5, switched on 2, off at 5. Now I won't worry so much about the circles after this. So, because I'm even going to be, like, you can't draw, I'll explain the problem with these vertical lines. I want a different color. So the problem with these vertical lines is that, say if I take this, say this could be maybe the 0.52 and the 0.51. 5 along the x, 1 along the y, 5 along the x, 2 along the y. This isn't the graph of a function because a function takes in one number and spits out one number. So it can't spit out 1 and 2. So this isn't the graph of a function. Now we're going to draw it like this because really we're only using it for UDLs. Technically speaking, the correct value is 5, 0, but it's not actually a big deal. It's not something for us to worry too much about. So here you can see for the 3ux, so u of x is just 0 and 1. So if you multiply those numbers by 3, instead of 0 and 1, you get 0 and 3. And similar story for this thing. This is a switch turned on at 2, switched off at 5. So it'll be 0, 1, 0 multiplied by 4. So 0, 1, 0 multiplied by 4 becomes 0, 4, 0. And in this way, you can form whatever kind of things you want, like between whatever 1.5 and 5. You can switch on with an x minus 1.5, switch off with minus 5. And if you want it to be whatever 19.2 kilonewtons, multiply both of those by 19.2. Well, technically, I suppose you're multiplying this by 19.2, but if you multiply out both of them, are getting there, right? Here's a question: what is the derivative of u of x? It's a kind of a weird question, but so look at the slope of the tangent. Now, basically u of x is similar to 3u of x here. So if you look at u of x here, the slope here is 0. Yeah, it's flat, and the slope here is also 0. So for u of x, most of the time the slope is 0. Now actually here the slope is undefined because the slope is, you have to be able to draw a tangent, but you can't actually draw a tangent here. But if you kind of mess around a little bit and just kind of argue, this is kind of funny maths. It actually took a long time for mathematicians to make all this work, but for us it's okay. If you were to measure how steep this was, you'd have to say it's kind of infinitely steep. It can't get any steeper than straight up. Now steepness in sense of derivative is slope is rise over run. Essentially here you have well, if it's u of x, the rise will be 0 to 1. You'll have a rise of 1 with a run of 0. It's kind of like 1 over 0. Now that isn't infinite. It's very messy. It's not really real maths. But basically it's kind of like infinite. It's about as steep as you can get. Now this does not make sense, but we don't have to go into that so much. But basically whatever we want to say is that roughly in a sense the derivative of the step function is this delta function. This is called the impulse function or delta function. Now what I've written down does not make sense, but it is possible to make sense of this. And you might say, how come you can differentiate u of x is a problem, but anti-differentiating delta is not a problem? You're just going to have to take my word on that. So if the derivative of u is delta, the antiderivative of delta is u. And this is what we're going to need. There is a more precise definition that can make sense of this. And basically what you can do is this thing, this infinite thing, you can make like a jolt. And maybe we'll get onto that a bit later when we talk about particular loads and why a delta function is going to be like a point load. Yeah, we'll probably talk about it a little bit later. I might actually forget, so it might be an example of something that you email a question about. You can also anti-differentiate the Heaviside function. So you can anti-differentiate the delta to the Heaviside, and you can anti-differentiate the Heaviside into something else. So let's see. So we got this Macaulay bracket. This is something that is pretty much only used in engineering maths. You'll see it in your structural analysis module next semester. Now it's kind of x by u of x. I wonder if we have a graph of it. I might need a graph on the next page. If there isn't, I will draw one. Yeah, I will draw one. So another word for this Heaviside is like a ramp function. So basically what it does is if you give it something negative, it gives you 0. But if you give it something positive, it spits out the same thing. Now you will have to get your head around this one way or another. So this is y equal to the Macaulay bracket of x. So you give it something negative, it spits out 0. The graph looks something like that. And then when you give it something positive, it gives back the same thing. Now y equal to x, because I'm saying, oh, put in something positive here that's x, you must get out x, so the output y is equal to the input. And this is of the form 1x plus 0, which is a line that cuts, so it's like mx plus c, cuts the y-axis at 0 here, and has a slope of 1, which basically means at 45 degrees, if the x and y axis are the same. So you could also call this thing a ramp function. But you will need this when you're going to be putting numbers in here. So for example, you'll have the square, I'll be calling it square bracket. It can't be a roundy bracket, it's a square bracket, it's a specific thing. If you start writing roundy brackets, I'm going to have to correct that. So if you give it a positive thing, it gives you the same thing back. If you give it something negative, it gives you 0. Yeah, and we're going to probably write it down on the next page. The antiderivative of the heavy side is the Macaulay bracket. Okay. Now in terms of a graph, what the Macaulay bracket does is whenever the thing is negative, it makes it 0. So I could draw something like this, could be y equal to f of x. Now it's positive here, so the Macaulay bracket is not going to give me anything different. They're supposed to be on top of each other. But in between these 2 points, f of x goes negative, and when you give it a negative into the square bracket, it gives you out 0. And then here again, the function is positive, so the square bracket of a positive function is just the same thing. So this thing here is the square bracket of f of x. So it chops off the negative part. And you could actually do that with just y equal to x as well. So y equal to x looks like this. Sorry, that should just be y equal to x. And so the Macaulay bracket of x, here it's negative, it gives you 0. And then after that, it gives you the same. So you need to know one way or another that the Macaulay bracket, when you give it something negative, it spits out 0. When you give it something positive, it just spits back the same thing you just put in. We have here that the antiderivative of the heavy side, the u function, is the square bracket. And you can just kind of prove it by writing the square bracket. You can show that, I must fix this myself. Just a bit of an exercise. So the thing inside the square bracket is positive if x is bigger than a. Because if x is bigger than a, that's the same as saying that if you take away a from both sides, x minus a is positive. These things mean the same thing. And of course the bracket says, if you give me something positive, I give you back the same thing, x minus a. Otherwise I give you 0. And so if you differentiate and do these two things, so this is like 1x minus a, well, whatever, a is a constant here. So differentiate x, you get 1, differentiate 0, you get 0. And look at this function. That is equal to 1 for x bigger than a, and 0 for less than a. Well, what's that? One for x bigger than a, 0 otherwise. That's the heavy side that starts at a, u of x minus a. So we have that the derivative of square bracket is u, so the antiderivative of u is square bracket. And you can show that it works similarly with the square bracket. What I'm trying to say here is that the square brackets are kind of like powers in terms of they anti-differentiate in the same way. So the antiderivative of square bracket to the power of n is add 1 to the power divided by the new power. And so say if you've got a square bracket, you can think of it as square bracket to the power of 1. The antiderivative would be square bracket squared over 2. Okay, now you have to be careful with like the square where you put it, and you have to use square brackets. Yeah, so as I said this. Okay, so we have some, well, this is great. We're going to finish this section. So this is the mathematical background before we start talking about the beams and really getting the link between the delta functions and the point loads, and between the heaviside functions and the UDLs. You can, if you want, like think of this delta somehow looking like a point, because the U's do correspond to UDLs, but that's not why they're called U's. Anyway, okay, so here's some very, very simple differential equations. So solve the differential equations. This means find y of x. Now there's something, we'll write down a little note here. So we're going to be anti-differentiating. So if we start with a fourth derivative, and we anti-differentiate it, we get to the third derivative. Now we'll explain this in backwards, it'll be a bit easier. Anti-differentiate again, you get to the second derivative. Anti-differentiate again, you get to the first derivative. Anti-differentiate again, you get y of x. Now every time you actually pick up a constant as well, so we can't forget that. Why is this the case? Well, take a function, differentiate it, you get dy dx. Differentiate the first derivative, you get the second derivative. Differentiate the second derivative, you get the third derivative. Differentiate the third derivative, you get the fourth derivative. So if this is differentiating in this direction, coming down is anti-differentiating. Okay. The other thing we want to show is from we've got on the previous page, if you start with a delta function and you anti-differentiate it, you get a u. So you'll have to get used to this thing. Anti-differentiate a u, you get a square bracket. Anti-differentiate a square bracket, you get square bracket squared over 2. Now what you're going to do is you're going to fix the constant here, which is a half, because it's divided by 2 is the same as a half. And the antiderivative of x minus a to the 2 is x minus a to the 3 over 3. And then you can fix the constant again, because you've got a half divided by 2 and divided by 3 is divided by 6. A half by a third is 1/6. And the antiderivative of x minus a to the 3, add 1 to the power, divide by the new power. Okay. So we'll do these fairly quickly, but remember we must pick up constants. So here, anti-differentiating both sides. If you anti-differentiate dy dx, you get y of x. We're going to anti-differentiate term by term, fixing constants. So we'll fix the 2. What is the antiderivative of u of x? It will be square bracket of x. Minus, fix the 2, antiderivative u of x minus 1 is square bracket of x minus 1. And then we pick up a constant. Okay, the next one. So this one, anti-differentiate both sides. So the antiderivative of the second derivative is the first derivative. Term by term, fixing constants. So fix the 3. Antiderivative of u is square bracket. These won't be in the tables, by the way, you'll just get used to them, because you can't really be going through a tables. Like, you'll be doing so many questions of these in this and next semester, you won't have time to look to the tables. You just get used to it. Plus the antiderivative of the delta function is a u function. And we pick up a constant. Now here we're going to be anti-differentiating twice, so we're going to have 2 constants, so I'll call the first one c1. Now we're not there yet, we have to find y of x, we have to anti-differentiate a second time. So if we anti-differentiate a second time, we get y, or y of x. I think I like y of x more. Again, term by term, fixing constants. Now the constants that we fix are the ones that are multiplying functions. So this 3 is multiplying a function, fix that 3. Antiderivative square bracket is square bracket squared over 2. Plus antiderivative of u is square bracket. Now, there's no constant here, or it's not multiplying, so it's not like you fix this constant. Now you could say it's a constant times 1, but you're going to end up with the same problem. So the question is, what do you differentiate to end up with a constant c1? If this was a 2 here, I trust us to say the derivative of 2x is 2, but this is just, instead of 2, it's c1, so it's like c1x. fix the constant c1, the derivative of x is 1, so c1 times 1 is this. So c1x is the antiderivative of c1. But we must pick up a second antiderivative as well. Okay, and one more just to finish off the lecture. So the second derivative here, we'll have to again antidifferentiate twice. So we get antidifferentiate, the second derivative, we get the first derivative, antiderivative square bracket squared. Well, what we'll do here is antiderivative square bracket squared is add 1 to the power, divide by the new power. Same for the other one. Add 1 to the power, divide by the new power. And we've antidifferentiated, so we must add a constant. And now we go again. From the first derivative, antidifferentiate, we get y of x. Now what I'm going to do here is, this is divided by 3. Dividing by 3 is finding a third. I'm going to fix the constant 1/3. And the antiderivative of x minus 2 to the power 3 is add 1 to the power, divide by the new power. Same story here, fix the 1/3, add 1 to the power, divide by the new power. And as before, the antiderivative of c1 is c1x. And as before, we've antidifferentiated a second time, so we need a c2. And then you could maybe tidy this up. 3 divided by 3 and dividing by 4 is dividing by 12. 1/12 x minus 2 to the 4. That's one way of writing it. The other way of writing it would be like this, that you multiply in. It's just that might make and if you had to antidifferentiate further, it would be complicated. But know that these are the same. Dividing by 12, multiplying by 1/12 is the same thing. And that's the mathematical background for us to start properly talking about beams here.